All right. Good morning, everybody. My name's Kallan Hart. I'm a graduate research assistant at South Dakota State University. Here representing my advisor, Dr. Mostafa Tazarov. I'm going to be talking a little bit about precast bridge bents with replaceable fuses. So first off, I'd just like to thank our industry collaborators as well as all of our funding agencies here for this project. It's been a pretty large project over the past 2 years, and we've tested quite a few columns. So I'll go into a little bit just to start, just a little bit of background on repairable precast bridge columns, and then I'll go over our feasible detailing and how we were able to rate those and choose which types of columns we decided to test before I get into our actual experimental study and then conclusions and future work. Just a little bit of background on these repairable precast bridge columns. We are trying to combine two different concepts. So bridge code right now requires life safety. Our goal, so bridge code, your bridge won't collapse, but you might have to repair it, you might have to tear it down after an earthquake. Our goal is to combine two concepts: advanced bridge construction connections, so that the bridge columns and other pieces can be precast off-site. They can be shipped there and built very quickly, so you don't have to close a road down for very long, as well as low damage detailing and repairability, so that after an earthquake, we're able to repair just one specific portion of the bridge column rather than needing to tear it down or really go into depth and detail with our repair. So that is how we will reach our low damage precast bridge columns. On the left there, that does show one type of precast bridge column connection. That'd be a grouted socket connection. And then on the right there, our concept with this repairable detailing is that we will use two sets of couplers on each bar to be able to remove the rebar in the plastic hinge region after it yields. So these types of columns are faster to build, they'll last longer, and should hopefully have a continuous functionality. So a little bit of difference between our conventional and repairable joints. Up in the upper left-hand corner there, you have just a conventional cast-in-place concrete bridge column showing your reinforcing steel bars. Then your column obviously is connected in one piece to the footing. So our goal is to use a precast bridge column there connected with two sets of couplers, like I said. At the base there, we have a steel pipe going into a steel socket that acts as a shear pin to take our shear forces and also allows the column to rotate. Then we are using buckling restrained reinforcement, BRR, as we call them. They're in the plastic hinge region. They're buckled in with two sets of couplers. And as you can see in the upper right-hand corner there, that's one of our BRR. So since the BRR are not covered in concrete there, the bars are likely going to buckle. So our goal to keep them from buckling, what we do is we are encasing them in a steel pipe and filling it with grout to hopefully keep that bar from buckling, but still allow it to act in tension. So what we do, since we want only the BRR to get damaged and not the column, we don't want the bars to yield or stretch in the main portion of the column. What we are actually doing is dog boning the steel bars there inside of the BRR. So we grind them down, reduce the diameter. So we use number 10 bars in these columns, but then reduce the diameter inside of those BRR to 1 inch. So it'd be like a number 8 bar, so that all of our yielding happens inside of the BRR and not in the main portion of the column. So we did go, we developed multiple different details. So I came up with 20 different kinds of details for these different types of columns with different connection types, all sorts of different concepts, all with the same basic BRR in the plastic hinge region. So that first one is just the most basic one, using the pipe pin connection. We have pipe pin connection using ultra high performance concrete. Ultra high performance concrete just uses, instead of aggregate in the concrete, it uses steel fibers, which helps give it a tensile capacity and can also push your compressive capacity up to 20 KSI. A large steel pipe there going into a steel socket, so grouted in, as well as other socket connections using post tensioning to help eliminate our residual displacement. So after an earthquake, we don't want our bridge to be tilted, so that tendon will hopefully pull it back into the center. So we came up with 20 of those. And then we used this rating chart from NCHRP report 864 to rate all 20 of those column alternatives and determine which ones we thought would be the best to test. So these are the top 4 columns that we have here. We have 2 pipe pin connection columns, one of them utilizing UHPC or ECC, a similar engineered cementitious composite in the plastic hinge region there, similar concept, just to reduce our damage in that area. Column 15 there uses the UHPC as well, and then is grouted into a socket as far as the column connection as well. And then column 19 would use post-tensioning tendons to hold the column in, or to connect the column to the footing. We were able in column 15 to also use post-tensioning tendons that would hopefully reduce that residual displacement, but then you are able to post-tension it off-site, whereas column 19 would have to be post-tensioned on-site to the footing. That would make it a little bit harder for your contractors. They need to know how to do that. So we rated them on a 0 to 5 scale. Those are the top 4 columns there. Columns 15 and 19 did tie. So we chose to test column number 3, 1, and 15. So our experimental investigation, we started out with a cast in place reference column, 9 feet tall, 8 feet up to the point where our actuator was connected. These are half scale bridge columns with 10 number 8 bars in the cast in place column. And we tested this under unidirectional cyclic loading, pushed it back and forth until we reached failure. So the first one of our repairable columns was RPH-PC. RPH stands for Repairable Precast Headed Column instead of cast in place. CIP was cast in place. PC is pipe in the column. As you can see, we have our pipe pin connection there. The pipe is in the column. We have our socket in the footing that it'll go into. So we have that reduced diameter neck section to allow for our BRR outside of it. We have threaded couplers from HRC, Headed Reinforcement Core, extending out of the column and extending out of the footing. We did include a circular shear or circular steel pipe there to hopefully reduce any compressive forces and damage that the base of the column would see. And on the upper right there, you can see our BRR bars before they were grouted into place. And you can see how we dog boned them to reduce that diameter. We did do 2 different dog boning lengths to see if that would have much of an effect. Hopefully a longer dog bone length would give you a higher displacement capacity. Shows just the assembly of that column as we went through, and these yellow fuses were our long dog bone length fuses. As you can see too, above the couplers there on the upper right hand corner, we did add some clamping collars and washers because there was still, the coupler needed to be able to move up and down in order to be threaded, because we had the female portion there on the headed portion of the bars extending out of the footing in the column, and then on those BRR headed bars we did have a male portion that was split and had to be screwed together. But then to eliminate any ability of the bars to buckle above that point, we added those clamping collars. We did find during testing, you'll see this in a little bit before I get to these other alternatives, we still experienced quite a bit of buckling. This column was successful, but we were trying to think, well, how can we reduce that buckling? Even there's a tiny gap there between the coupler and that yellow steel tube. We had a significant amount of buckling there. So we were thinking, how can we get rid of that? One idea was to use a type of fuse that is tension only. So what we did is we worked with Headed Reinforcement Core to actually develop a coupler that works with a steel tendon instead of a rebar. So this is our next column here, RPH-PF. So this was one of the other alternatives. PF just stands for pipe in the footing. We decided to flip the pipe, put it in the footing. RPH-PC was tested before these other two, so we kind of came up with some new ideas there. So we changed our pipe to a square because we did notice some rotation when we were pushing that RPH-PC column back and forth. So we changed it to a square. We also, like I said, flipped and put the pipe in the footing. That way the socket won't get any water in it now, since it's upside down. We don't, especially in cold environments, if you get water in there, it might get rusty, it might freeze. So, and then because of that, we were able to develop the socket, as you can see on the upper right hand corner, with threaded rods, so that we were able to weld a high strength nut into it. And then we're able to screw those threaded rods in to reduce any gap between that steel pipe and the cup. In the other column, it was really hard to reduce that gap. We'd put some shims in there, but it's hard to get your fingers in there, and we don't want a soft start. So that eliminates that. By soft start, I mean the initial stiffness of the column as you push it back and forth. If there's a gap there, it'll kind of slide before it hits the side. So on the upper left there, you can see our threaded coupler with the wedge that's standard in the pre-stressing industry and a 0.6 inch diameter steel tendon. So we were able to connect this column, as you can see on the bottom right there. We were able to screw those threaded rods in to eliminate any soft start in the column. We did cover the tendons up with some plastic tubing just to ensure that they wouldn't rupture while we were doing any crack marking and injure anybody. The third column was RPH-NP. This was a post-tension column. NP is no pin connection. We used a grouted socket connection. As you can see there on the bottom right corner, we used steel culvert as our socket connection. We did have to increase the size of the footing up to 3 feet tall, which reached the capacity of our lab and our crane. So you can see the column on the bottom left there, which had the couplers on either end. So there were 3 column cages. That column cage on the upper left there is our column cage for the center portion there in the reduced neck diameter section. We did, as you can see, bend the bars in to create a plastic or to create a rebar hinge. We were worried since the other column just had the other columns had a pipe pin connection. They were able to rotate. With this one, now we have bars extending between the 2 halves. We didn't want our force capacity to jump up too much. So we bent those bars in so that hopefully they wouldn't increase the force capacity. On the upper right there, we are post-tensioning all 15 of our 0.5 diameter steel tendons. They were only post-tensioned to 25% of the yield. So we don't want those tendons to yield at all. Hopefully they'll just help us pull it back and reduce any residual displacement. So you can just see the construction there. We lowered it into the socket and grouted it in with high strength grout on the bottom right-hand corner. So when we got to our testing, we observed a couple things. So at 1% drift here, you can already see the cast in place column on the left has quite a few cracks. The other 3, I did forget to mention RPH-PF and RPH-NP. We did go with UHPC in those alternatives. So those are ultra high performance concrete. We were hoping not to see very much damage. So RPH-PC, a little bit of cracking there at the base. RPH-PF, we do have 1 crack above there, but we determined that we think that crack actually came from erection and not from the testing itself. RPH-NP, there was no visible damage at 1%. By 3%, CIP is already starting to spall. Bits of concrete are falling off. RPH-PC, a decent amount of cracking up in that main octagonal section and quite a bit of spalling at the base as well. Whereas RPH-PF, RPH-NP, we are hardly seeing any damage at this point, thanks to that UHPC. At 5% drift ratio, CIP is experiencing significant damage, lots of spalling at the base there. RPH-PC, as you can see, those bars are starting to buckle. They are pushing outwards. So it was still a successful column. We wanted to think about how we can eliminate that. Those clamping collars there, we did eliminate any gap between the couplers and the column. But because of that, when it was in compression, as you can see, there's quite a bit of spalling up in that octagonal section because those clamping collars were pushing on the bottom of the concrete and caused that to crack. So with RPH-PF and NP, we did not have that issue at all. We did include those clamping collars just in case. We determined that in the end, they were not necessary in those 2 columns while using the tendons because they do act only in compression. We were able to leave quite a bit of gap between the tendons and the rebar heads as well. At 8% drift ratio, CIP, even more spalling than before. RPH-PC, significant buckling. Again, those are the green fuses. So that was after we repaired it. In the first test, we pushed RPH-PC to 5% and the other 2 RPH columns to 4%, which is past the design earthquake for downtown Los Angeles before repairing them. Still very limited damage in RPH-PF and RPH-NP. You can see the red marks there are the cracks in that second set of testing. And at capacity there, CIP, we did push it to 10%. We experienced some rebar fracture at about 10% there with quite a bit of spalling. RPH-PC, we did not see any rebar fracture, but significant buckling of those BRR bars, despite our best attempts to prevent that. RPH-PF failed at 8% by rupture of the tendons. The one issue with the tendons was they're much stronger. They have a much higher force capacity. They're 270 grade compared to our grade 60 rebar, but their displacement capacity, their strength capacity is a little bit less. So we were expecting to see a little bit less displacement capacity. In those last two columns, we did also increase our number of bars to 14 from 10 to try to match the force capacity, since we were using 0.6 diameter tendons. Even though they had a higher force capacity, the diameter is the area is quite a bit smaller than our dog boned 1-inch diameter bars. RPH-NP, we did not fail any tendons. What actually happened is those neck bars, despite bending them into a rebar hinge in the neck, they ruptured at high drift. So we did at 7% rupture quite a few of those neck bars, and our force capacity dropped quite a bit. So one of our ideas to eliminate that would be to debond those bars as they are extending into the footing. This just shows our force displacement response here. So you can see the black line is our CIP column. Then we did test, the blue there is our RPH pin in the column, which used the BRR bars. As you can see, it had a similar force capacity, similar displacement capacity there. You can see the dotted line is the original test. Well, the second line shows our repair. So our stiffness did decrease quite a bit. So that was one thing we were trying to hope in the last two columns to kind of eliminate. But even as you can see in the red one there, once we use the tendons, our stiffness decreased even more with those tendons. I think we noticed that there was quite a bit of slip of those tendons in the pre-stressing wedges. They do a great job of holding on, but once you put it in a compression, they're not quite made for a cyclic loading. So when you push them back and forth, they do kind of tend to slip. But that isn't necessarily a bad thing, because it did help us to reach a very high displacement capacity. And then in the green there, we did show our RPH no pin column with the grouted socket, which had quite a bit of stiffness degradation just due to those bars in the neck likely yielding. We actually just tested that column a week ago, so I haven't gotten through all of the data yet, but I'm guessing those neck bars did yield in the first test, but we did not see, as you can see in those first two dotted lines for the green and red, we did not yield any tendons in the first sets of testing. This just shows our cyclic hysteri, our test data here for on the upper left would be RPH-PC versus CIP, and then RPH-PF and RPH-NP, as you can see there, with both the original testing and then the -R would be the repaired. So just in conclusion, repair of RPH-PC BRR at 5% was difficult due to bar misalignment. So we did have that bar buckling, so we needed to use the actuator to push the column back to repair and put in our new sets of BRR. So that is not something you can do in the field. You can't create an earthquake to fix your bridge column. So that's why we decided to use tendons in place of BRR. So that, and we were able to repair it with 2 workers. It took us about 3 hours to repair all 14 tendons, replace them. So it was fairly quick. With a good construction crew, you could repair a bridge in a day. Use of tendons in place of the BRR did eliminate a residual displacement, while the UHPC in those last 2 columns significantly reduced any damage. They did have in our other pin connection one with the UHPC, we did have slightly lower force and displacement capacity in those tendon columns as compared to the other one using BRR. RPH-PF, or our pipe in the footing one, the square one using the tendons in the UHPC, had the least amount of damage due to that UHPC. We were actually looking to test it a 3rd time. I'm graduating here this May, but Dr. Chazarv is hoping to order some SMA tendons and test it a 3rd time. So that column was extremely successful, very little damage, all the way up to 7% drift capacity. But it also had the least amount of stiffness degradation, but also the lowest stiffness overall compared to the other columns. So in the end, repairable columns showed lower damage and similar displacement and force capacities compared to the CIP. They're very successful when we were able to repair them. So